So what do you think of when you imagine a black hole? Maybe a voracious consumer that eats planets for breakfast? Or even a tear in the fabric of the universe that future astronauts could use as a shortcut to galaxies unknown? My name is Rebecca Lewis. I'm a post-baccalaureate researcher with the UCLA Galactic Center Group, and I'm here to answer the question, what is a black hole? By definition, a black hole is a region of spacetime where gravity is so strong that nothing can travel fast enough to escape its pull, even light. A black hole has mass like any other object, but it's also only a single point in spacetime. That means it has no length, no width, and no height because a point has no physical dimensions in space. So, if a black hole has mass but it doesn't have a physical size, why do black holes look like they have a shape? Well, we use the term event horizon to describe how large a black hole is. Physically, the event horizon, also called the Schwarzschild radius, is a distance away from the black hole at which you'd need an escape velocity exceeding the speed of light in order to escape the black hole's gravity. The event horizon therefore defines the point of no return. Any light that crosses the event horizon is trapped. And because light can't travel in one side of the event horizon and out the other, the event horizon looks like a solid and opaque sphere, even though physically it isn't. This also means that black holes are not the predators of the cosmos. They don't go out searching for things to eat, and they don't suck things into them like a vacuum. Things just fall into them. It's similar to how a meteorite can be pulled in by Earth's gravity and fall into its atmosphere. Astronomers organize black holes into classes that depend on their mass. The two main classes of black holes are stellar mass and supermassive. First, stellar mass black holes can have up to 100 times the mass of our Sun, and they form at the end of the lives of massive stars. During a star's lifetime, it produces radiation through the process of nuclear fusion. The radiation made by nuclear fusion presses outward from the core of the star, and the star doesn't explode because the star's gravity keeps it contained by pressing back inward. But at the end of a massive star's life, it runs out of fuel for nuclear fusion, and all that's left is gravity. Gravity makes the dying star collapse in on itself, and the core of the star becomes a black hole, while the outer layers explode in a supernova. Next, at the other end of the mass spectrum, we have supermassive black holes. These giants are 1,000,000 times the mass of our Sun, or more, and observational evidence suggests that they are found at the centers of most large galaxies. Unfortunately, we don't have any well-evidenced theories yet for how this class of black holes form. Our own galaxy, the Milky Way, is home to the supermassive black hole Sagittarius A star. It's about 4,000,000 times the mass of our Sun and lies in the Milky Way's galactic center. It was discovered when astronomers at UCLA watched the motions of stars in the galactic center and noticed that they moved in ellipses like planets orbiting around a sun. Even though we couldn't see Sagittarius A star itself, we were able to use the observed orbits of the stars to pinpoint its location. Another famous supermassive black hole is M87 star. It's at the center of the supergiant elliptical galaxy M87, and it became the first black hole with its picture taken in April of 2019. The picture itself was taken using the Event Horizon Telescope, which is a global array of radio telescopes. The glow around M87 star comes from its accretion disk. The accretion disk is a disk of material orbiting the black hole and slowly falling into it. The disk glows because parts of it rub against each other as they orbit and heat up due to friction. M87 star is also much bigger than Sagittarius A star. While Sagittarius A star is about 4,000,000 times the mass of the Sun, M87 star is 3,000,000,000 times the mass of the Sun. It's important to note that the radius of a black hole's event horizon is directly related to its mass. So, if you double the mass of a black hole, you double its radius. That means that when we compare a stellar mass black hole to a supermassive one, the supermassive ones have event horizons that are at least 10,000 times as large as stellar mass black holes. In science fiction movies, black holes are often used as portals or shortcuts to other areas of the universe. However, black holes are better described as dead ends in space. When an object falls into a black hole, the side of the object closer to the black hole experiences a greater gravitational force pulling on it than the side facing away from the black hole. Imagine that your feet are pointed toward the black hole with your head away from it. This happens when you stand on Earth. Your feet are closer to the ground and so experience a greater gravitational pull than your head. However, the gravity of a black hole is many times more powerful than Earth's gravity. So if you fall into a black hole, the difference in pull between your feet and your head gets larger and larger. And eventually the black hole starts to pull you apart like taffy, with your feet being pulled away from your head. It pulls and pulls until you're just a trail of atoms swirling into the black hole. Essentially, you're being stretched out into a string of spaghetti. So this stretching process is justly called spaghettification, and it happens to everything that falls into a black hole. Well, I hope this answers a few of your questions about black holes, and make sure to check out the Galactic Center Group's other videos if you want to know more about how Sagittarius A star was discovered, or about the technology that we use to view the Milky Way galactic center.